Okay, let's begin today. It's 9:01. 딱 1분 지났는데. So I hope everyone will be coming soon. 오늘 많이 안 왔네. So this week, next week will be last week of the course, 그죠? Next week will be last week of the course. After that, we will have so in 3 weeks, we will have your final exams. And I start getting the questions when it's going to be the final exams. I think it's going to be not on Thursday or Friday. The official final week is not next week. Next week's starting from Wednesday, I think. Wednesday. In Korean briefly. 아마 기말고사 기간이 다음 주 말고 그 다음 주 수요일부터 시작일 거예요. 그 좀 애매하게 돼 있어갖고 목요일에 목 시작하라고 그러더라고요. 월, 화, 수는 혹시 보강이 필요한 경우 보강하라고 비워놓은 거고 수업은 다음 주로 정식으로는 끝나고 근데 그 주에는 안 볼 것 같고요. 그 사람들 질문들이 좀씩 와서 그 주에는 안 보고 그 다음 주 돌아오는 월요일 정도가 되지 않을까 싶어요. 확정되면 그거는 이번 주나 다음 주에 다시 알려줄게요. 맞지? 내가 저번 주에 다시 한번 학과에 확인했는데 그때가 맞더라고. So the final exams most likely to be in Monday in 3 weeks. In 3 to 4 weeks, 3 weeks. So I will let you know for the final exam schedules. And I also put up a assignment 3 solutions, open the Easy Hub so you can double check your solutions for your previous assignment. Assignment 4 is due on when? 언제지? Next week? This week? Next week. It's only a small number of questions, so I'm sure you'll have no problem to finish it. I might give you another couple more questions for your final exams. So if so, I will try to give it to sometime this week. Okay, just be aware. Okay, anything else? 혹시 다 잊어버린 거 질문? No? Okay. 이번 주는 월요일부터 피곤하구나. 이상하다. 그죠? So let's pick up where we left off. We've been discussing on binary search tree. Binary search tree. It's a tree. It's a tree that simply put as if you can go left if your key is less than the value that you're comparing to, then you should go to the left. If your key is greater than the value that you're comparing to, then you should go to right. In that way, you will have some type of sorted tree in it. So what was the time complexity of a searching operation in this type of sorted tree? This is binary, so what was the order log n or order height was the general answer to the part, because every time you make a decision, yes or no, less or bigger, and then you only take 2 approaches. So overall, you'll be dealing with the log 2 of n, where n is the number of nodes in the tree. That was the basis of what we have been discussing in binary search tree, right? What was the common data structure that we can implement using this binary search tree? What was the one data structure they mentioned in the beginning of this chapter? Dictionary, right? Dictionary. So in your textbook implementations, I also said a few times last class, in your textbooks, they mention it like they are comparing their keys. At the end, they are inserting or not deleting, searching for the elements according to that key. But what did I say about textbooks implementations? It's okay to think of as key representing the element value as well. So if you look at it as both things are same, then textbook implementation is much more simpler to understand. That was one thing, because textbook wanted to emphasize on the dictionary part more. That's why they were saying like inserting a pair instead of inserting an element. Okay, but it's the same thing for us. So this was a search. I think that was it. I think that was mostly we've been discussing insertion. 또 뭐였지? Insertion code for implementation according to the textbook. So this was a search operation. Search begins at a root. If the root is null, the search tree is empty, the search fails. So those basic steps that we described, right? I also ask you to take a look at some of the implementations in your textbook too, right? What was the search? I'm not gonna say everything, but while 뭐 이렇게 썼었지? I'm just practicing myself too. While p is not null, if something like if key is less or bigger, less, 맞나? Key is less than p's key, then what do? P going to p's left. Of course, it's much more. Other smaller steps are there too, but it was like else. It means, and then they're gonna test. Why am I testing like this again? In terms of textbook implementation. 미안, 원래 이렇게 하는데. Who's doing this? When you're actually writing a program, who's doing this? It's a personal preference, but I prefer this way. 이렇게 하는데 이렇게 하면 나중에 또 매치하기가 힘드니까. Anyway, else, what are they doing here? Again, 뭐였어? Why are they just simply if and else, left or right? Why aren't they doing that in your code implementation? 왜 그랬지? Yeah. They wanted to check whether there are equal values or not. 그죠? 맞나? 맞지? Key is greater than P's key. 그죠? If so, then P goes to P's right. Else, then what? It's an equal value. So you're returning. You could return a value, or you could just simply say, yes, I found it. Yes. 그죠? It's a very basic search operation of your textbook's implementation for this is search. So easy. 그죠? It's not too bad. 왜 그래 처음 본 사람처럼. Did you guys take a look at the example that I wanted to take a look at for the deletion part? I think it was 14.6. 14.6. This is 14.4. I mean, I think this is the first time I actually wrote a code like this in class. I mean, I always assume that you guys know very basic part. I just wanted to make sure that everyone is in the same page. 그지? 그죠? You guys only have a week to see me. 이제 그래봐야 다음 주면 쫑이에요. 그래라, 알았어. Insertion part. So basically, when you go to left, when you go to right, when you hit the elements that you're looking for, you're done. That was the part. Obviously, this also take a order of height, which is order log 2 of n. This is 14.4 program look like. It's not exactly look like this, but I mean almost same. I mean class definitions P. What was a P? Why are we using P in this case? I think they put P something like 뭐였지? P. Yeah. Where does this P start from? Where does this P start from? 그죠? Root. 그죠? I also ask you to do a practice like following one by one. If you testing code like this, 이건 뭐 이렇게 돼 있던가? Root? Root must be somewhere else, or you have to tell the root, in the beginning of the function where the root is. You can start doing like this. So this is my P here. I'm in the root. So while P is not null, I have some value 5. 이거 5 하면 넣으면 안 되겠다. 20, 15, 14, 17, 25, whatever. Okay, I'm looking for search. 뭐할까? 17? Search 17. 나 이거 하기 싫은데 한 번 더 하는 거거든? 다 아는 거 같은데도 그냥 한 번 하는 건데 마지막으로 한번 봐줘. Search 17. 그죠? So, okay. P is root. P is right here. I'm doing P is not null. P 20 is not null. So okay. Go to next one. If my key is 17. 이렇게 써요. Key 17. P's key. I treat as key and value same thing. P key 20. 그죠? I usually write it like this, side by side. 편하니까. So I don't forget where I'm in. 20. 그 다음에 key less than 17 is less than 20. Okay. I'm in here, right? P is left. P is pointing to a P's left. Now this is my new P. 그죠? This way. So I'm in 15 now. Okay, P's left. Done. I'm not going into here. Going back up. The P is not null. Testing P is not null. No, P is still 15. So it's not null. If key is P's key, 뭐야? P key. Key. What is key again? 17. P's key here. 15. Key 17 is less than 15? No. So I go to else. Testing again. Key is 아니야. 헷갈려. 17 greater than 15. Okay. I'm in here. P's right is my new P now. 그죠? I did this one more time. I'm going back up again to the root. And my key is now 17. Okay. 17. I cannot make a decision. 그지? Out. Else. 17 greater than 17. Cannot make a decision. Out. 17 is 17. If I'm in here, it's the same thing. Returning yes. Yes, I have 17 in my binary search tree. Done. So my final value will be yes. It's 17 is here. You can return a value like this, or you can return a pointer to 17. Doesn't really matter whatever you wanted to do. So I was saying like this, if you want to keep track of your programs like this is one way. I'm just showing you in some case, some people are having trouble how to look at this, how to keep track of things. Of course, if you want to do this for the recursive functions like this, it may not be a good idea. But it's one way of doing it. So if you have a binary search tree, if you wanted to print out the values in the ascending order, what was the function called for printing out the value for ascending order? In order. How do you do that again? 맞아. Left root right. they call it as ascending function. 맞나? Ascending? Ascend. So basically, I start from the root. I'm gonna call it in order. In order root. In order some node. Okay. Left root right. Left root right. Left. So inside in order. And left. Root. They use the term visit. Yeah? 아이고, 거꾸로 막 포인터가 거꾸로 간다. Right. Something like this. We have discussed this for a long time. Imagine you try to do that in writing like this. You have to repeat your code many times until you don't find any elements left in it. So you should know how to write this. I may be bad. I would remove entire part and asking you to fill it up. Okay. And simple tweak was possible to do this for insert. What was it? Again, what was a simple trick the textbook was using? 뭐 이상한 거 PP was there, right? They try to give you extra pointers. Again, it's pointing to a same thing. And those they put it like 뭐지? PP. I think PP was null at the beginning. Every time you start from something, you like PP equal P. PP, 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 right? So insertion need to be done where the search ended. That's the place for the element that I'm looking for. Is it? No, yes, no responses. 순간 딴 생각했다. 이제 나도 하다가 딴 생각하는구나. PP. So, well, I think in the insertion part they did the very similar stuff, and then after the loop they did what? Another very simple step was what? 뭐였어? 이건 insert고 내가 이거 insert. Let's say I'm inserting 16. So if I do this key 16, 16, 16, when I'm here, key is P's key left. Key 여기서 key 16. P's key is what? 17. 그죠? No, yes. 17. Right here, key is 여기서 걸리는구나. Key is 16 is less than 17. P's left. Do I have my left? Do I have this? No. So, if your pointer is empty, what's their value? 이렇게 되면 P. What is this case? What is this? Null. So now P is null. Remember, PP is still here, right? P is null. Okay, go back up. My only condition is P is not null, but P is null. Break the loop. PP still pointing to 17. I think someone asked me this last class. Where is PP pointing somewhere here, or I'm pointing to a root position here? So after this, they do this again for the part. 뭐 여기서부터는 뻔하지 뭐. Something like I'm gonna use PP. My key is less than PP's 뭐야? PP's 뭐야? 아니지. If key, I'm comparing key. PP's key. And then left. 그지? key. 왜 그래? 헷갈리게. 맞죠? 똑같은 거잖아. 그지? So I'm inserting PP's left should be the 16, the new one that I'm giving to. Okay? left key. 미안. key. 책에는 이렇게 돼 있을 거예요. key and value 이렇게 해갖고 new element 이렇게 해갖고 else, but you guys got the idea. PP's right key. 그지? key. 여기서 여기로 가는지 여기로 가는지. So that case is 16 is less than 17, so I'm gonna add a new node here, 16. 이거 끝나고 이렇게 가죠? That was what? That was insertion part on it too, right? You could have done this inside somewhere, but there are many different ways of doing it. This is one way of doing it. Textbook just simply give you the extra pointer to do this. Makes sense. Makes sense. I don't think any other examples in your textbook so far. 이거보다 어려웠을 리가 없을 거야. 이거 어렵지도 않. 이것도 안 어려운데. Any chapter, any implementation that we have looked at so far, probably it's not more difficult than this. 이게 뭐야? 챕터 14.3, 챕터 14인데 챕터 1부터 13까지 나온 뭐 구현하는 거고 뭐 이런 것도 다 이거보다 어렵지도 않고 이거보다 쉽지도 않고 똑같아요. So I just wanted to know, I want you guys to know that this is how to think like one and do the practice on your own. Okay? So this was another stupid example they give you. Where is the position for value 35? Where should be inserted? Where should be inserted? 뭐 그냥 눈으로 봐도 you don't have to do this, but with your eyes you know where 35 should be in. Again, I'm probably not going to give you questions like this. You don't need to know this. I mean, if you're given a tree like this, you can just do it in your own eyes. I'm not going to ask you questions like this. I'll probably ask you questions like more like this. Okay? 이건 뭐 이걸 몰라도 눈으로 봐도 할 수 있는 거니까 이런 걸 물어보진 않겠지. insert 어디다 하냐? 그렇진 않겠죠. Deletion maybe. Deletion sometimes confusing. Deletion may be confusing because you have to deal with the 3 different cases. If you do a preview, then you will see what I mean. If you do a deletion of the leaf, if you do a deletion of the degree 1 node, if you do a deletion of a degree 2 node, even if you're doing a deletion of a degree 2 node, but it's in the between the elements, so those cases you have to cover for deletion part. That might be a bit more tricky. Not tricky, just you need to cover all the cases. So let's take a look. 이거 해야 되나? Inserting element with this key 7, 27, blah, blah, blah. After 7 should be below 8 on the left side. Done. 왜 넣어놨을까? I don't understand why I put this. Insertion elements with the key 18, 20, 10, 15. On the right side, 18. Okay. Just do practice once. On this way, like 이렇게. Okay. Then you will never forget about this. You will never miss any of the sentences for your implementations. Like I told you, because it looks simpler because they give you the solution right away. For example, if they don't give you a solution at the beginning, it might be tricky. 예를 들어 지금 우리는 코드를 보고 이걸 적으니까 되게 쉬워 보이지. 예를 들어 코드를 안 주고 적으라 그러면 고민을 좀 해야 되겠죠. 고민해도 이렇게 깔끔하게 안 나올 거야. 아마 막 왼쪽으로 갔다 오른쪽으로 갔다 다시 돌아갔다 별의별 코드가 다 나올 가능성이 높아요. 그러니까, 보고 참고하는 용도로 쓰세요. 좀 사족이긴 한데 좀 다른 얘기긴 한데 우리 책에 나오는 알고리즘들은 말할 필요도 없고 그 웬만한 여러분들이 앞으로 필요하거나 쓸만한 알고리즘들은 그 자기가 고민하려고 하지 말고 책 또는 인터넷을 찾아서 잘 써놓은 코드를 잘 이용하려고 노력을 좀 해요. 굳이 내가 머리가 훨씬 더 좋으니까 이거보다 더 잘된 걸 내가 굳이 처음부터 짜서 써야지 그런 실수들을 많이 하는데 굳이 그러지 않아도 돼요. 특히 우리 레벨에서 나오는 거는 다 있어 다. 그러니까 잘 가져다 쓸 수 있는 가져다 쓰려도 자기 거에다가 갖다 붙이려면 많이 고쳐야 되겠죠, 그죠? 그러니까 그런 버릇을 좀 들이려고 해봐요. 그래서 그냥 답을 막 주는 거니까. Okay. So finally, the operation delete. Bit more tricky, just because there are more cases to cover. I mean, this is first step that they. First step for any functions or any program that you want to write. Make sure your program doesn't fail on any of the inputs. I don't know what's my tree going to be look like, so I have to cover all possible cases. Hopefully, when we cover these 3 cases, my function works as it planned. So element is in the leaf. Deleting this will be quite easy. What do you have to do before you delete something? Can you delete something that doesn't exist in the tree? No. Probably the first step you need to do is search. That's the first step. Just like the insertion part. But deleting a leaf is quite simple. As long as you found one, you just simply disconnect this line pointer. You just delete it from the memory. Delete can be other stuff too. Or elements in the degree 1 node. Degree node, no degree. Let me remind you again. If a node has one child in it, then it's degree 1 node. After this chapter, we're going to go into a graph chapter. They will try to discuss in different names for the node degree, sometimes outbound, inbound. So when we get to that, I will explain a bit more. But at this point, if the node have one child like this, then 17 is node 1 degree. Node 2, node like this, 15, 2, 22. So it seems to be much more complicated if I delete this. If I delete this, what should be my next step? 16, 17, 14. If I decide to delete 15, I mean, without looking at the solution yet, what should I do? 어떻게 하면 될까? Well, I could pick one of them to bring it up. For example, if I put 16 up, then nothing has to be changed, right? I mean, just looking at the cases. But textbook nicely tell you which cases I have to put which one what. So it's more of a selection process. which node to select if I delete a one like this. If I delete a leaf, there's nothing to select. 그죠? 리프 지으면 뭐 위에다 끌어올릴 게 없으니까. So this time let's take a look at case by case. Case 1, deleting from a leaf. We can simply discard the leaf node. Example, delete the leaf element key 7. Okay, let's do this. Search, 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 search. Seems 17 is there. So whatever means possible, I keep the record. I keep the location of 7. I probably keep the location of its parents too. So I can disconnect 7 from its parents. 예를 들어, if I remember the location of a 7, it doesn't mean anything. I have to update the pointer of an 8, yeah, right, in order to successfully delete this. So I might need to remember the location of a 7's parents. Or if you have a backward pointer, to its parents, then you might need to just remember position of 7. You can see that there are multiple ways of doing this, multiple ways of implementing this. Which one is better? I don't know. It's up to you. Which one? My experience, usually which one that you can think of clearly. 그냥 자기한테 제일 편하게 할 수 있는 방법. 머릿속에 계산이 잘 되는 방법으로 하면 돼요. 뭐 러닝 타임이야 뭐 얼마나 차이 난다고. 뭐 솔직히 돌려봐야 컴퓨터를 돌리면 크게 차이 안 나요. 눈 깜짝하면 끝나는데. Okay. So 7. Disconnecting pointer from 8. 그죠? This was quite nice. It's standing out. Next case, little leaf with the key 35. So I have to look at the position of 30, which is parents of 35. I just simply disconnect. What does it mean to disconnect? How do you represent a disconnect in this case? Null. If I'm assuming P is pointing to 30, P's right equal null. It simply means I'm extracting the right node of 30, nothing. So I have to delete 35 in different ways. If it's a class, I have to deallocate the memory location. 35가 저장돼 있던 저장소를 날려야지. Delete, destroy functions that we discussed in previous chapters. I mean, every ADT definition that we looked at, class definition, they also had some 뭐 이런 거 있지 않았어? Class node, and then they have something like 뭐 이렇게 해가지고 destroy 뭐 이런 거 있었죠? If you look at the functions inside, they usually say delete that memory location. Delete means also deleting that memory from the from the program. That's case 1. I don't think there is sophisticated cases for deleting a leaf. Leaf usually very simple. 여기서 이제 하나 미스하면 프로그램이 바뀌는 거지. 혹시 생각지도 못했던 리프 뭐 이런 게 있다. 근데 리프는 아마 거의 다 커버한 것 같아. Those of you came in late, I was mentioning for short times for your final schedule exams. 뭐냐? Deleting from a degree 1 node, no degree 1 node. Okay, what am I deleting here? Which node have a degree 1 here? Let's pick 40. 40 seems to have a degree 1. What do? Delete 40. Delete 40. One way you could do is I'm just checking that I don't have anything on my right. Maybe I could just simply pointing to its parents, its children, sorry, children, like these. 20 is just directly pointing to a 30 because this is just degree 1 node, 40 is degree 1 node. If it's a degree 2, I cannot do that. It's 3 looked like a triple format. So I don't know which one to select to do this. This is one way. That's one case. Degree 1 node, in case of deleting degree 1 node, I'll be pointing to the node, I'm pointing to the children of the node that I'm trying to delete. 40's children, I'm directly pointing to it. How do I write that in the code? 뭐 어떻게 해? 40's. Let's say 40 is P. 20 is PP. PP's right equals P's left. So delete P. delete P. done. 그냥 루트에 right를 P의 left로 연결해주고 P 날려버리면 tree is still connected, nothing else getting distorted. 그죠? So questions like these, even if you cannot write it 100% like these, if you show me your ideas, then I would probably give you at least half of mark or probably 80% of the mark. 비슷하게만 쓰면 내가 뭐 syntax 틀렸다고 점수 깎고 그렇진 않으니까. It's one way to look at it. Let's kill it and do it. Still, deleting from a degree 1 node. Deleting from a degree 1 node, let's try to delete 15. 어떻게 해? Likewise, 15's children. So I'll probably check which side of 15 has a child in it. 15 has a left child or right child? Right child. So in the code, I also have to check it, which one is not null. If found a not null one, I'm going to connect it to it. So 10's right will be a 15's right because 15's right is not null. 이렇게 써놓고 보면 편하지. 이렇게 써놓으면 되게 쉬운 것 같죠? If you take a look at the size of the code for 14.6, deleting the node, it's a bit longer than the other two because it's a simple paragraph. It's a simple block of code. Each one taking care of each case. Okay. What about deleting a node with a node degree 2? This might be tricky, but it seems that maybe it's a good idea. Just pick one of the child that may be the largest, smallest, and then bring it up to the position where I deleted. Might be the idea. 아래서 될 만한 거 하나 끌어와서 위에 붙여주면 될 것 같죠? 그죠? 근데 될 만한 게 무슨 뜻이야? Which one to select? Luckily, they give you the solution for this. Let's try to delete a key 10. Key 10. Okay. That's right there. That's degree 2 node. 10 right there. This is way left. Replace with the largest key in the left subtree. Or the smallest key in the right subtree. Let's pick one. Either way is fine. Replace with the, so if I'm in 10, the first approach, I'm going to take a look at the left side of the tree, left subtree. What is the left subtree of this 10? How do you find the largest key among the subtree? Largest key among the subtree. How do you find the largest key? Huh? Yeah, you just keep going to right. You keep going to right until you don't have until you meet a null. Right here. So I'm gonna bring up 8. I'm gonna choose 8. Or how do you find the smallest node in the right subtree? Right subtree is here. Smallest is what? 왼쪽. But in this case, 15 seems to be the smallest because it doesn't have any left child in it. So either way is fine. Either way is fine. 설마 저 코드는 안 해도 되겠지? How do you find the largest key in the left subtree? 어떻게 해, 여기서 if I change something? 뭐 이렇게만 해서 계속 가도 되겠죠? I don't need this. 이렇게 해서 keep going to left. If it's null, then I break the loop. That's the position I'm pointing to. 아래 거 필요 없지? 계속 왼쪽으로만 가면 되니까. 아, 이것도 필요 없네. While p left until you hit the not null part. Largest key, replace the largest key. 왼쪽에 largest key면
맨 처음만 왼쪽 가고 그 다음엔 다 가야 되는 거 아니에요?
아니 여기서부터 이렇게 오니까 아 이거 미안 여기 left가 아니라 right이구나 미안 right 미안 이거 봐 안 하면 헷갈려 말로만 하라 그러면 right 시작을 여기로 주고 이렇게 하면 시작이 여기야 여기가 아니라 left subtree 그러니까 루트가 여기야 6부터 시작하는 거야 6에서 right 오케이 여기서 이렇게 갔다 이렇게 하는 게 아니라 알았지? 헷갈리지 마요. 그래, 그거 헷갈릴 줄 알았다. 처음에 left로 갔다가 right 찾아 내려온 게 아니라 아예 시작할 때 루트를 6을 주고 시작하는 거예요. 그럼 right만 가는 거니까. 오케이? Left subtree, right subtree, left subtree, right subtree. So root of that each tree is 6 and 15. So I don't need to go left first or right first and do that. Okay? 아이고 괜히 다 줘버렸네. Shoot. Okay, which node is the largest key in the left subtree will be 8. Yeah? According to that, maybe if I wrote a code like this, keep to the right and then 8. 8 now going to a position 10. How do you do that? Things are, so how do I do that? Largest key must be in a leaf or degree 1 node. So I can bring so I need to take care of 8 children. 8 children will be 이렇게 되면 똑같지 않아? 8을 여기 올려야 되니까 8을 지운다고 생각을 해보면 노드 1 디그리 지우는 거랑 똑같은 코드 비슷하게 되지 않을까? 그죠? 노드 1 디그리 지우고 insert 8 하고 거의 비슷한 insert 8은 아니겠다. 노드 1 하고 So large key must be in a leaf or degree 1 node. 그럴 수밖에 없지. 타고 내려오다 보면 끝나는 게 leaf 아니면 더 이상 오른쪽으로 갈 수 없는 경우니까. So 7 will be a new right child of the 6, which is the parents of a 8. 복잡다. And then 8 will be moving up to the position in 10. 그렇죠? 10, 8 절로 가고 하면 6, 7, 8 done. Nothing has to change. So this is case for the selecting the replacement node that is largest among its left subtree. 이거 코드로 짤 생각하니까 끔찍하지. 근데 비슷해. 책에 보면 똑같아요. 지금 얘기하는 게 똑같아요. 여기서 크게 달라질 것도 없어. 달라질 것도 없어. 포인터만 left, right로 새로 저장만 해주면 똑같아. So case 3 is still case 3, deleting a node, degree 2 node, node degree 2 node. 뭐 많이 나온다. Note that the node with the largest key in the left subtree as well as the smallest in the right subtree is guaranteed to be in the node with either 0 or non-empty subtree. Okay, has to be non-empty subtree. How can we find a node with the largest key in the left subtree of node? 이건 뭐 thing I just explained. If you keep following the pointer of the right child of the root of the left subtree, then you will have the largest key, smallest key in the right subtree. You just follow the left pointer of a child of child, then you will ending up the smallest part. 그렇죠? 이거 알고 있는 설명한 거예요. 이거 쫓아가는 거. 맞지? 내가 잘못하는 거 아니지? 응?
노드는 포인터만 끊지 말고 노드 자체만 냅둬요.
포인터를 끊지 말고 노드 자체를 냅둔다는. 노드는 그냥 메모리에 있는 거니까 포인터만 이렇게 슥슥 바꿔주면 되죠. 예. 그림은 이제 꼭 이렇게 바꿔주는 것같이 하지만 사실 포인터만 바꿔주면 노드 자체는 그대로 냅두고 할 거예요 아마. 굳이 원하면 지웠다가 다시 해도 되는데 뭐 굳이 그럴 필요는 없으니까. 이게 어떻게 보면 좋은 질문이야. 그러니까 지금 하는 게 이게 우리가 그림을 저렇게 그려놓고 해서 그렇지. 막 8번은 여기 있고 10번은 여기 있고 막 이거를 우리가 포인터만 계속 이렇게 바꿔주는 거예요. 뭐 이렇게. 그래서 실제로 그려놓고 보면 저렇게 나이스하게 트리 포맷은 나오지 않죠. 그러니까 굳이 안 지워도 되는 거예요. 포인터만 왔다 갔다 하면 되는 거예요. 이 다음 챕터에 그래프 하면 나와요. 그래프 하면 나와요. Another case for the deletion part from node degree 2 node. Replace with the largest key in the left subtree. Let's try to delete 20. What is the largest key on the left subtree? Well, 10, 15, 18. 18. Bring up 18 up, but it's a leaf node, much simpler case. Cut it, go up. Done. Time complexity of a delete is order of a height, order log n. Why do they say time complexity of deletion is still log of n? Huh? Why? Yeah. Probably textbook give you much more difficult explanation, but what I see is only thing that I need to do in here is just finding the largest one or smallest one. That's how much I go down on my tree, right? It will be much one step less than my height in worst case. See? And then after I found my element, it's the same thing as search. The time complexity of search is log of n. So after I find my node that is to be replaced, I just simply change the pointers. This operation is nothing. This is constant operation. 그치? 이건 it's not log n or anything. So overall time complexity of deleting something is still log of n, log of height. 말 되죠? 그죠? 몰라. 비슷할 거야. search complexity 하는 거랑 delete 하는 거랑 똑같을 거예요. 그냥 단순하게 생각해. 단순하게. 컴플렉시티 하면 쫄지 말고 단순하게 생각해. 내가 얼마만큼 트리를 왔다 갔다 하느냐. 트리 문제가 아니더라도 내가 얼마만큼의 비교를 하느냐. 그걸로 단순하게 생각하면 오히려 쉽게 답이 나올 수 있어요. So that's why we call it as time complexity of delete is order of height. see more examples on 14.4 or program 14.6 for the deletion operation code. Okay, let's take a look at 14.6. But it's just pretty much repeating what I just explained here. This coding ways, same thing. I'm not going to write it all again, but I'm just going to look at this structure of a 14.6. 나도 14.6은 너무 길어서 못 외웠어. 그대로 책에 있는 방법, 내 방법대로 하면 대충 하겠는데 책에 있는 거 너무 길어가지고. So I also have to take a look. The first part, they looking for, first thing, they looking for the one they try to find, the one they try to delete. So they do a searching first. Searching first. In which way? They just do it normal ways. If you go to left, right, until you find one. Otherwise, you're going to return P is a null. Search first. And then next, they're doing a, the first thing they do is handling no degree 2. No degree 2. No degree 2. 뭐 뻔하지. If they know where to delete it, so inside and here, they give you the position of, it's the same code. It's the same thing as a search code. 똑같아. Position of a P where the thing should be deleted. At this point, they actually finding P's right until they find the 뭐지? Largest on the left subtree. They get the key. 똑같아 그리고는. And then they just change the pointer. 뭐 할 게 없어. I wanted to do this, but there is nothing I can write. It's very similar to the search operation. Search operation. 아까 전에 search 쓴 거랑 insertion 할 때 포인터 바꿔준 거랑 똑같아요. 똑같아요. So that's why I want you guys to take a look at the 14.6 as a preview. If you take a look at it, you will see a no difference. No difference. One thing later, after they do this, the last part, they actually do a handling, no degree 1. 3 part. Same, 3 part. Searching, changing pointer. As soon as you find the, 나 계속 헷갈려. Largest one on the left subtree. This is quite simple code. While P is not null, P equal to P's right. See? So whatever you find, replace. Change the pointer. P's left, P's left is now P's right, stuff like that. And here, just no degree 1. 이거 뭐, you just simply pick out the ones you found out the node to delete, whether you find out whether it has a children or not. They're checking like if P's left is not null or P's right is not null, one of them is not null, you will be connecting to the parents node of a new child. 적고 싶어도 별로 적을 게 없어. 적고 싶어도 별로 적을 게 없어. Are you sure all these cases will cover every single possible tree in this case? 이거면 다 커버가 될까? 모든 트리 케이스가 요거 3개 이렇게 적으면 다 커버가 될까? How do you know? How do you know that you cover all the cases? How do you test your code is okay? Usually I do this. I bring out the very common trees, couple of them, testing deleting 1, no degree 1, deleting no degree 2, And then I try to come up with the very extreme cases with the no degree 2. 되게 복잡하게 보일 만한 것들 한두 개 해서 여기다 테스트에 넣어봐서 뭐 되면 되나 보다 하고. If you're lucky, then you'll be okay. But some people might come up with some very, very extreme cases. Then your function may be broken. So if you found that another special cases that your program doesn't fit, then that's the point where you go back to your code and start fixing it. 내가 생각지 못한 케이스를 발견을 대부분 이렇게 할 거야. 이렇게 해놓고 웬만한 건 다 되니까 하다가 혹시 내가 미스한 케이스가 나오면 그때 가서 다시 고치면 돼요. 그게 뭐 잘못된 거 아니에요. 그런 식으로 코드를 업데이트하는 거예요. Okay, binary search tree with the duplicates. We can remove the requirements that all elements in the binary search tree need the distinct keys. If you can change the code that we have looked at so far to handle a duplicate keys, if you wish, duplicate keys. It means that we can have a binary search tree saying that doesn't have all the keys doesn't have to be distinct. If you want to handle those situations, there are very simple steps to change in your code that we looked at so far. Simply those less than or greater signs, you insert an equal signs. Smaller than or equal to, or larger than equal to. Then that's okay too. 아까 전에 비교할 때 뭐 이렇게 돼 있고 이렇게 돼 있는 거예요. 이렇게만 해주면 the duplicate key they will handle a duplicate keys. Of course, you need to change a little bit at the end, but this is the step for those part. For us, it's okay. I don't really care too much, but they just give you a very simple solution on that part. If you made those small changes, then binary search tree can have a distinct duplicate keys. Okay, that's it for binary search tree. Wonderful tree, fast search, nicely organized. Node can be printed out as ascending order with a simple tree traverse functions like in order, or deletion part was a bit tricky, but if you think about it, only 3 cases covering deleting a leaf node, degree 1 node, degree 2 node. But degree 1 node is just getting your child to your parents. That's one step. Degree 2 node, selecting the largest element on your left side of the tree, put that into the position, or selecting the smallest key on your right subtree. That's the only thing you need to do. And of course, search and insertion is basis of all those operations. It's just simple changing of the pointer stuff at the end. Hopefully, that gives you ideas for how to handle and manipulate these trees. 다 했지? Any questions? 다 했지? 다 했지 물어봐도 대답도 없고 뭐 안 하면 어떡할 거야? 안 하면 어떡할 거야? 책을 봤었어야지 내가 다 했는지 안 했는지 알지. 그래. If you take a look at the books on the chapter 14, at the end of last chapter of chapter 14 is last section of the chapter 14 is covering some of the applications of this this binary search tree, but that's for fun. If you want, you can take a look at it. I'm not going to cover it in class. Just like queue and stack examples, after we just explain how these work, then they try to give you different problems for using those data structures, right? Same thing. So you can take a look at it for binary search tree as well. They exampled as 어려운 거다. First one is histogram. Histogram is not that much. Second one is best fit bin packing algorithms. 빈 패킹 알고리즘 어디서 나오나 혹시? 아마 쿠즈노 교수님 과목에 나올 수도 있어요. 아마 그 알고리즘 컴퓨터 알고리즘 하는 쪽에서는 안 나와? 그럼 모르면 속이 편합니다. 몰라도 돼요. If you want, you can take a, it's only one paragraph. You can read a bean packing problem for that part. I think bean packing problem is also one of those problems as to be called as 뭐야? NP hard problems. Bean packing problems. Okay. So I'm gonna go into this. I think this is chapter 16. I'm gonna jump into chapter 16. 계속 트리만 나오는데 let's jump into 16. And then if we have time, then I will go into a AVL tree, which is chapter 15, I think. So if we have time. Graph. From this chapter, you can relax a little bit, just have it as own reference to it. The reason I'm covering chapter 16 for graph part, some of you will never take this course covering graphs. So I just want you to know there are something like this exist. And there are a bunch of people who try to solve a problem on top of this graphs. 이걸로 먹고 사는 사람들도 있다는 걸 보여주기 위해서 하는 건데 조금 뭐라 그럴까. 이거 하는 사람들이 참 대단해 보인다. 돈은 못 벌어요. 내가 알기로는. 학교에 가지 않는 이상에. 근데 뭐 좀 특이한 거 한번 봅시다. Graph terminologies. I mentioned many times. So many of you are familiar with the terms. Vertex, edges. Vertex I usually call it a node. Or sometimes I draw a dot. Edges. The line between a vertex, covering line between the vertex. So if I draw a tree like this, vertex, edges in the between. Similar terms are being used. Adjacent, the node that is connected to. Adjacent means you're close, right beside you. So I might say this one is adjacent to this one because they are connected. So those definitions will come and how to look at it. And degrees, incident is also another term that you have edge coming in, coming out of you. 이거 완전 신세계예요. 나중에 또 하다 보면 이거 완전 또 신세계예요. Degrees, we know degrees. How many edges that is coming out of you as you are one of the vertex. Cycles. What is a cycle? We mentioned this too. What is a cycle? 아니다. What is cycle? 순환. How do you define a cycle? How do you define it? What is the condition for determine something is cycle? Yeah. Another way of saying it, cycle 어떻게 그려? Let's say you're starting from here. This is P1. Let's say B1. B1, B2, B3. B2, okay, B1. Next one, B2, B3, B1. In the past that you can write, if you see yourself one more time, then it's a cycle. So that's a definition of a cycle. In the past, you will encounter the same node one more time. Cycle. Is it good to have a cycle? Trees have a cycle? No. But if I add it's no longer to be a tree, but maybe like that. I can break the cycle stuff. Connected components or spanning tree. We'll take a look at what it means. Type of graph. Undirected, directed, weighted graph. 많다. Graph representations, adjacent matrix, array adjacents, linked list, adjacents. This sounds to be very fancy. It's simply say it's a way of implementing graph. This on using your data structure. Simply means one of them will be using a list. One of them just simply, which means the array. The other ones can be used a linked list to represent this graph. Graph searching methods, breadth first and depth first. 저 하나? Maybe we can take a look. So algorithms. when we're discussing a graph, and mostly the algorithm that we are discussing on top of graph is like this, finding a path. I like to get to B1 to B3. Which path do I have to go through? So there is a bunch of algorithms finding a path or a connected component. If I delete a one edge, then my graph will be connected. Something called bridge. Can we find the bridge in a big graph? Graph mark. How do you find it? Spanning tree also. You like to have a core component of a graph. How do you find those things? So algorithms are mostly covering this part. Okay, I'm gonna stop here today and we'll continue for the next class. 추석 부르자, 추석.